All right, welcome back. So today we'll be talking about still in continuing Ampere's law. So we look at Ampere laws last time, but we'll be continuing talking about that today. And then we'll talk about magnetic forces between two conductors. Okay, so let's jump in here. So last time when we talked about Ampere's law, that this is something similar to Gauss's law, in which that you can use Gauss's law to calculate the electric field. And now Ampere's law applies to magnetic field, in which here Ampere's law says that so the magnetic field parallel to the path for the small segments of path, and then you sum over all the whole closed path of the field that should be equal to a constant number mu naught times the current enclosed. So this constant number is the permittivity of free space, which is equal to 4 pi times 10 to the minus 7 Tesla times meters OA. And then we look at the application of that to a straight wire. Magnetic field produced by that straight wire should be curving around that wire, but you can use your right hand rule to determine what's the direction of the magnetic field. So your thumb goes in the direction of the current, your four fingers curve in the direction of the magnetic field. So that's the right hand rule number 2, which you can call the right hand rule number 1 in the for the direction of the magnetic force earlier that we talked about. B field, magnetic-wise, is mu naught I over 2 pi times R. So if you are further away from the current, you get smaller magnetic field, okay? And proportional to the current I. So today we'll be looking at the, if you have a loop of wire that carries current. So in this case, this loop carries current here. Now, similarly, you should have an electric field generated, right? So at any given location here, 3 locations showing here, you'll see that, let's talk about this one here. So your thumb points in the direction of the current at that location, particularly should be in its tangential direction. Your 4 fingers then will curve in the direction of the B field, okay? So B field, it's along the direction of the fingers. And then if you're over here, you do the same. B field will be here, and then the same here. So you can see for the loop here, inside the loop, you have the magnetic field just pointing upward. Okay, but if you're outside the field, then your finger will actually curl backward, so it's going to be downward outside of the loop. Okay, so if you draw magnetic field lines, they will look like something like this. Okay, for the magnetic field lines. The magnetic white. So this is a little bit hard to derive, so you'll be looking at the B field times the um, times the delta L. You divide a closed path into different segments and then do that. Or this is actually you will have to use your calculus knowledge, but because this course is not calculus based, so I'm not going to do that. But as the result, at the end, this is similar to a straight wire, but you do not have a pi, okay? So in the denominator, so it's just mu naught I over 2 pi over 2r instead of 2 pi r. For a straight wire, it's over 2 pi r. For a circular loop at the center, so this B field is at the center of the loop, okay? So right at the center of the circle will be mu naught I divided by 2 times r for the um, radius of the loop. All right. Now, a lot of times you will have a lot of loops stacking up. So a device called solenoid is something like this. You have a wire, you wrap it around a cylinder. So then here you have many loops stacking up, hundreds, sometimes maybe even thousands of loops stacking up in that case, okay? And then if you send through the current there, you'll generate magnetic field around here. So for each loop, let's say if you send currents through here, and then going this way, so you can use your right hand rule again at any given location, right? So it's going to curve, let's say at the top of here for one of the wires, the current direction is pointing out towards you, and your four fingers will curve in the direction of magnetic field. So the magnetic field should be going in this fashion, like indicated in the figure over here. Okay, and then the same thing if you go to the bottom here, you could do that. You'll see the magnetic field will be pointing in the direction as indicated in the figure here. So in that case, you'll see that actually inside the loop over here, you get straight parallel magnetic field lines. That means magnetic field inside here is very uniform. They are parallel to each other. Outside over here, right outside the solenoid here, actually you will not have magnetic field lines. So that means electric field right outside the solenoid is going to be zero. Okay, and then it start to increase when you are going outward in that direction. So if you look at a magnetic field line like this for the solenoid and then compare to a bar magnetic, okay? So the magnetic field goes from the North Pole to the South Pole in a sense, and then inside that will be going from South Pole to North Pole. So this magnetic field produced by a solenoid is similar to a bar magnetic, but in this case, this is the magnetic field produced by electric current. So this is called an electromagnetic. Okay. Um, so to calculate the magnetic field produced by a solenoid, so we are going to just look at the one of the cross-sectional area. So you imagine there's a solenoid like this, and then if you cut vertically through the center of it and cut it into half, then you'll see current on top will actually point towards you, and then current at the bottom over here, it's gonna point into the paper, into the screen. Okay, so in that case, if we draw a closed loop like this, rectangular shape, so inside the solenoid and then perpendicular to the solenoid, and then outside the solenoid and then perpendicular to the solenoid. Again, if we do the B field times those four segments, and then add that map. So the first one, side one will be this guy times delta L. So B field times delta L, which is parallel to each other. And then side two will be the B field in this direction times the change H over here. But in this case, because B field is just in the horizontal direction, it does not have a vertical component. So B field in the vertical component will be zero. So this side two will be zero. Just right out to the side outside the solenoid, B field will be zero again, so that guy's zero. And then 4 is similar to 2, so then that will be 0. So overall, these three segments of B times delta L add up will be just equal to B times L here. And according to Ampere law, that should be equal to mu naught times the current enclosed. Okay, so for this rectangular loop, it encloses these currents. So you can actually count how many. So it's n numbers of current there. So you multiply by n. So mu naught ni here. So then the B field you can calculate. You divide both sides by L here. Gets you the B field, the magnetic field, equal to mu naught n I divided by the length L. Okay. So this is how many turns you have basically. And then divide by L, that will give you density of turns per meter. Okay, so small n for density, but if you do that capital N over L times I, that will also be fine. Okay, that will give you the magnetic field inside the solenoid, and SI unit for that will be in Tesla. Okay, all right. So let's take a look on one example on solenoid. So it says to construct solenoid, you wrap an insulated wire uniformly around a plastic tube 7.6 centimeter in diameter and 33 centimeter long. You would like 3.0 amps current to produce a 2.5 kilo Gauss, G for Gauss, okay? For Gauss and Tesla, so they are both used to as the units of magnetic field, but one Tesla is bigger. One Tesla is about 10,000 of Gauss, okay? So that's the conversion factor there. It's asking you what's the total length of wire you need to meet this these specifications, okay? So this is a solenoid, and we know that for a solenoid, it's B field, right? B field is equal to mu naught, you can flip a couple slides backward, but mu naught times capital N over L times I, or just mu naught small n times I, where small n will be equal to capital N over L. Okay. Um, so it's given you that this guy is given 2.5 kilogauss. Okay. So which will be using this conversion factor, that will be 0.25 Tesla. Okay. So 0.25 um, Tesla, and mu naught is constant, and it gives you I. I is 3 amps. Okay. And let's see, this guy is a known. We know that. And now it tells you that L is 33. Okay, so I think we know L. Okay, so we know L is 33 centimeters. So you will convert it into meters, 0.33 meters. Okay. Um, then you can see from this equation over here, you can calculate number of turns you have, right? So, and number of turns, and then you think about a solenoid is something like this. There's a circular cylinder like this on the ends, okay? And then you wrap it around over and over and over and over again, like that, okay? So there's n turns. If you know n turns times, um, so if you do n turns times, oops, too much. Okay. So if you do n turns times the circumference of each turn, which is ID, and it's giving you diameter, so we're going to just use ID, okay? Then that will be equal to the total length of the wire you will need. So I'm calling this small l, okay? So in this case, we can see you can do n times pi d to get your L. So your small l then should be equal to m from this equation over here should be b times L divided by mu naught I. Okay, so b times L divided by mu naught I, and then times pi times d. That will be what the length you needed. Okay, so 0.25 Tesla. Let's put everything in SI units so we don't have to write units right now. Times L 0.33 in meters, okay, times pi and times D 0.076, okay, over mu naught, that is 4 pi 10 to the minus 7, okay, and times I times 3, okay. So you can plug in all these numbers into your calculator and then calculate. Okay. So one thing you don't have to is the pi, and pi actually cancels. Okay. So that at the end will give you 5.2 times 10 to the 3, and this should be in SI units or meters. Okay. So that's on that. Okay. All right. So basically, starting with this equation, and then we know the total length will be number of turns times the circumference of each turn. Okay. All right. So next, we're going to look at the actually magnetic forces between two parallel conductors. Okay. So we know that if you have a wire that carries current, then it will produce a magnetic field. Now, if you have a second wire nearby, so then second wire is carrying current, then it's now in the presence of magnetic field produced by the first wire. Okay. So we know that a current carrying wire inside a magnetic field will experience magnetic force. Okay, so we can determine first what will be the magnetic field produced by the first current, I1, at the location of I2. Okay, so using your right hand rule, your forefingers, your thumb points in the direction of current, and then your forefingers curve in the direction of the B field. So in this case, B field will be going in this direction of the circles like that. And then for the second one, now it's inside the magnetic field. So at the location of here, this is pointing into the paper for the magnetic field. Okay, so for magnetic field, it's pointing into the B field at the location here. It's actually pointing inward. Okay, or you can say X. Okay, and there. Now, if we use our right hand rule to determine the direction of the magnetic field on the second wire here. So your thumb goes in the direction of the current, which in this case is upward, and then your forefinger goes into the direction of the B field, which is inside into the paper. So your palm is facing towards the left, so that means your B field is pointing to the left. Okay, so in the case, so B field will be pointing to the left, which is towards the original wire, so it's attractive force. Okay, and B field you can calculate produced by a wire will be mu naught I divided by 2 pi r, right? So in that case, R is the distance between these two wires, and then for force of the second one is IL, which is I2 now times L times that B field. So putting all this together, you'll get mu naught I1 I2 L divided by 2 pi r. And in this case, that would be the force of 2 experienced by 1. And if you're looking other way around, forces of on 1 by the magnetic field produced by 2, it will be the same amount of magnetic, but it will be in opposite direction. Attractive force will be pointing in that direction. Okay, so that will be pointing in that direction, that they should be attractive. Here is the a top view of the configuration over here. So B field is pointing into the paper. This is upward, okay, on the top, and it'll be in this direction, okay. But on this guy, it's going to be in this direction, but the same magnitude, okay. Also, you will also see a lot of times people will be just interested in just the force per unit length, because the wires could be parallel to each other by infinity long. Okay, but if you look at a particular segment, then it will be just force divided by length. So then L would go to the other side of the equation. So then it will be equal to just mu naught I1 I2, okay, I1 I2, and then over 2 pi r in the case. Okay, so just without that L. All right. Now, if you have two wires carry current in the opposite direction, then you can do the same analysis to determine the direction of the force. It will turn out that if the two are in opposite directions, then the force will be repulsive. Okay, so it will be pushing away from each other. Okay, you can use your right hand rules, kind of having a practice on that. All right. Let's take a look on a couple examples here. So let's look at the first one first. Okay, so this one says two long straight wires are separated by a distance of 9.25 centimeters. So your R, this is your R, is that, okay? And centimeters, so it's going to be converted into meters for the SI unit. It says one wire carries 2.75, so that's your I1. Okay, so this guy is your I1. And then the other one, this guy is your I2. Okay, so this is your I2. Carries net amount of current. It says find the force per meter. Okay, so this is why I said just force per meter. So then you'll be looking at F over L. Okay, so F over L will be just mu naught I1 I2 over 2 pi r. Okay, so basically just plug in numbers because you have all the numbers you need. Mu naught is the 4 pi 10 to the -7, and I1 is the 2.75, I2 is the 4.33, okay, and divided by 2 pi times R, 9.25 by centimeter, so convert into meters is -2, 10 to the -2, okay. The pi and pi actually will cancel again, 4 and 2 will partially cancel because 2. So then you probably don't have to plug both numbers into the calculator, but just 2. Okay. So this will give you 2.57 times 10 to the minus 5 newtons of force. Okay. Or you can say this will be 25.7 micronewtons if you like that better. Okay. But this will be just fine. So that's your part A. Part B is asking you if the force per meter exerted on the other wire greater, less, or same as. Okay, so we know this is going to be the same because it's the interaction between two wires. So Newton's third law will come into play. Okay, so it's a action and reaction pair. Okay, action and reaction pair of force. Pair of forces. Okay. All right. And second one. So it says find the direction and magnitude of force per meter. Okay. Again, force per meter that the right bottom y experience. So this y experience. Okay. So there are three wires here. So this is a kind of need a little bit explanation here. So these are the three wires. Lay on horizontally, perpendicular to the screen here. So this one carries current that is pointing towards you. These two carries current that's going away from you. Okay, so into the paper. So this one is out of paper. These two are coming into the paper, going into the paper. Okay, equal lateral triangles, each side 10 centimeter. Okay, so we are looking for the force on this guy. So these two wires, their currents are opposite to each other, so that this force would be repulsive. Okay, so force by that one is going to be pointing in this direction, repulsive. Okay, so in that direction. All right. And for some reason, I always get like when I try to do the straight wire, it's not always going to give me straight wire, but let me try it again. Okay. So it's kind of wavy in that case, okay? And then current by the force by this one to this guy due to the magnetic interaction will be now pointing towards each other. That's going to be attractive force, okay? So that goes in that okay, direction. All right. So there's this F1 and then there's this F2, okay? So vectors. I know you guys don't like them a lot, but looks like we have to stick with them for a while. Okay, so and I should draw this guy shorter because oops, what did I do? Okay, because it's between 5 and 10 should be less than between 10 and 20. Okay, so this guy will be then about half. Okay, of F2. Let me see if I can. Now, yeah, there's always issue with drawing sideways or at the angle, but we try again. Okay, I think that's the best I can have. Okay, so F1 there, okay. Force per unit length, again, is F over L. So for the magnitude of F1 is, and then we say F1 over L, okay. It's equal to mu naught um, mu naught I1, I2, okay. So maybe I can call this I3, and then this get to be I1, this get to be I2, and that's I3. Okay, so I1 then I3. Okay. I1 I3 over 2 pi r. In this case, it would be the 10 centimeter. They are both the same. So we do 4 pi 10 to the -7, and then I1 is 5, I3 is 20, okay, divided by 2 pi times 10 centimeters is 0.1 meters, okay. So for that, I1 over L is going to have a magnitude of 1 point, oh, just 1 times 10 to the -4, okay. So 1 times 10 to the -4 newtons per meter. Then there's cancellation, pi and pi, and then 5 times 10 is 100, and 4 divided by 2 is going to be 2, or actually, let me see, do I have the numbers wrong? 10 and 20, 5 and 20. Okay, so it looks like I have wrong numbers somehow on my notes. Let me see. Fine. Okay, great. Okay, so it's gonna to be 2 times the, instead of 1, but 2 times 10 to the -4. Okay, so I have to go without notes right now. Okay, so that's 2 on that. Now F2 over L, just the magnitude. Okay, so again, it will be 4 pi times 10 to the -7. 4 pi times 10 to the -7, and it's 10 by 20, 10 times 20, okay, F I1, I2, I3 over 2 pi R again, 0.1, okay, so again, pi cancels. On the top, we have 2 times 200, so that will be 4, okay, so, and then over 0.1, that means that's like times 10, right? So to the top, so 200 times 10 is 2000, okay? And then 4000, because 4 over 2 will be 2. 4000 times 10 to the -7 will be 4 times 10 to the -4, okay? Newtons per meter, okay? All right, so now we can do the x component of this guy. Okay, so according to geometry, this guy should be like 60-degree below the horizontal. Okay, so you can do F1 cosine to the x direction, and then F1 sine of 60 to be the y. Okay, so you can do F1 in that case, and then add F1 x to the F2 x. F2 will be purely just in negative x direction, and then F1y plus F2y, F2y will be 0. So you go get total forces component x direction, y direction, okay? And then you'll do the x component square plus the y component square for the magnitude, okay? And for the directional angle, you do tangent inverse, okay? So this is, again, going back to the um, vector thing, okay? So let's see if we can do that. All right. So maybe I don't think I have a next page, but I have it probably here. So let's try it again. I'm quickly going to just say how to find those. Okay, so there will be a F1. Okay, so F1, and then there will be an F2 about twice long as that one. And then earlier we say F1 over L, the same, just a random L. There will be mu naught I1. So this guy is called I1. This guy is called I2. This is here I3. I1, I3 and then over 2 pi r. So 4 pi times 10 to the minus 7, and then 5, and then 20, and then over 2 pi times 0.1. Okay, so pi and pi cancels. So this will be 2.0, 10 to the minus 4 newtons. Okay, and then F2 over L is going to be 4 pi 10 to the minus 7 times 10 times 20. So it's basically twice of F1 over L. Okay, so that will be 4.0 10 to the minus 4 newtons per meters. Okay, yeah, per meters as well. And its direction over here, it's 60 degrees. Okay, because it's equilateral triangle in that. So F1 L times cosine of 60. Okay, so which will be half. Cosine 60 is half. Half of that should be 2.0. Okay, times 10 to the minus 4 newtons per meter. Okay, and this is the F1x, okay, over L. F1 over L sine of 60, but should be minus because it's pointing kind of downward. Okay, so that should be so sine of 60, you can put it into the calculator and then times. So it's the 4.0 10 to the minus 4 times sine of minus 60. Okay, so that would be I'm gonna to do this quickly, but 3.5-ish. Okay, negative sine of 60 degrees, 3.46 times 10 to the minus 4. This would be again newtons over meters. Okay. So this is your F1 of y over L. Now F2 of x over L is gonna to be just that whole thing, but in negative direction. Okay, and then F2 of y over L is 0. So your total force of Fx over L should be F1xL, which is this guy, plus F2xL. Okay, so 2 minus 4, so minus 2. Okay, so in that case, minus 2, 10 to the minus 4, here 10 to the minus 4 newtons per meter for the x component, and then the y component total L will be the F1y plus the F2y, which is 0. Okay, so F1y is this guy, but negative. I forgot about the negative there, so this would be negative. Okay, so it'll be just negative 3.46 times 10 to the minus 4 newtons per meter. Okay, and for the total, we'll do x squared plus y squared. So F total per unit length should be square root of just minus 2 square, and then plus negative 3.46 square. Okay, total together times 10 to the minus 4. Okay, and that will equal to square root minus 2 square plus minus 3.46 square. Okay, and that will give you about 4.0 times 10 to the minus 4 newtons over meters. Okay, so that's the magnitude. And direction wise, it's going to be tangent inverse of the y over x. Okay, So y is minus 3.46 times 10 to the minus 4 over 10 to the minus 4 will actually cancel. Minus 2 minus 2 down here 0.00 um, minus 2. Okay, and that will be tangent inverse 3.46 over 2, and that's about 60 degrees. Okay, so about 60 degrees. So in this case, now your x component is negative, right? So remember your x component is negative. We need to add 180. Okay, so add 180. So then it's negative 240 degrees for the directional angle. Okay, so these two should add up to be somewhere in this direction. Okay, so that's the total force. So it should be in the third quadrant. So because x and y are both negative, okay, so then the angle should be in the third quadrant would be that angle there. Okay, all right. So let's see if I can capture all the solutions in one screen. Okay, all right. So that's pretty much what we learned today. So we look at the Ampere's law again, this time to apply to calculate the magnetic field at the center of loop, which now you don't have the pi. Okay, so for the straight wire, you do have the 2 pi, the pi down there in the denominator, but this is a loop, so it's kind of like opposite. When you have straight wire, you need a pi. When you have circle, you don't need a pi. Okay. Magnetic force between two parallel conductors for force per unit length will be mu naught I1 I2 over 2 pi r. Okay, and again, this is a vector, so we'll follow the vector additions doing x, y component in that case. Okay. All right, that'll be it for today. I'll see you guys next time. Bye bye.